Good morning, everyone. I'm Deng Sicong. I'd like to present our work on normalization of early modern French texts. This project focuses on building reliable models for converting archaic spellings into modern standard French using a transformer-based architecture. So let's begin with the motivation. French texts from the 17th and 18th century are full of inconsistent archaic spelling. Without fixed rule at the time, writers use phonetic or regional variants, making these texts difficult to read, search, or analyze digitally. At the time, the writing style emphasized elegance and sometimes with exaggerated spelling. This happens especially in literature and academic circles. Therefore, normalization helps resolve this by converting the surface forms into a standardized, readable version of modern French that we're familiar with. And also, it is crucial that modern NLP tools requires consistent input. But then that brings the question, what is normalization? Well, by normalization, we don't just mean spelling correction that basically all modern computers are capable of. It's about converting outdated forms into their modern equivalents while preserving meaning and structure. So, a more appropriate analog to me would be monolingual translation. Therefore, you will actually see that our methodology is similar to that of translation. And now, let me walk you through an example of what the normalization process looks like in the practice. We have here a scanned fragment from the Gazette, which is a material that we used in the project. And below it, we have two parallel texts of this very image. The middle section shows the 17th century transcription, which includes archaic glyphs like the long F, shown in blue color, irregular spelling such as the bientôt, and also typographic features like the ampersand, shown in yellow, and ligature, showing also blue color. And below, we present the normalized version, what we consider standard modern French orthography, following the pre-1919 convention, which to today, the widely used convention in school and publication. We believe this example demonstrates how our model not only learns to modernize vocabulary and spelling, but also handles historical typographic variations. And with all the background information on normalization and historical French, let's talk about the process pipeline. Our process pipeline divides into 6 parts. Firstly, the image acquisition, where we gather the scanned historical images exactly like the one we shown before. Then, all the images goes into the OCR process with tools like Kraken and Katamari, which yields the raw data. And the raw data will then go to the pre-processing, that is the cleaning and filtering, through which we have a washed clean data. And with those data, we will build a custom subword tokenizer, which will then be used in the model training. And finally, we have the evaluation with different metrics shown here. As discussed before, to train a robust normalization model, we need high-quality parallel data, pairs of historical and modern sentences. Fortunately, there are now server-aligned corpora for historical French, though still fewer than, for example, Latin or English. Our work builds on the free EM corpus, which aligns 17th and 18th century French texts with their modern equivalent. It is one of a few large-scale sentence-aligned resources of its kind, with carefully curated example. And in addition, we incorporate the Gazette, a richly lexical and stylistically coherent periodical, which provides a consistent editorial voice across a wide chronological span. And as a newspaper, it exhibits a variety in theme and vocabulary, which makes it a wonderful material for normalization tasks. The broaden linguistic coverage will also include other aligned corpora, such as the filter corpora. Together, these sources form a corpus that is both thematically diverse and orthographically rich, ideal for training models capable of generalizing across registers. And again, these resource texts are not born digital. They come from scanned historical documents, and the quality of OCR directly affects downstream performances. We use in this practice Kraken and Katamari, two open source OCR frameworks fine-tuned for historical French. Katamari is especially adaptable for domain-specific training, while Kraken offers ensemble prediction that boosts robustness on integrated print. And here we have an image showing the actual workflow of OCR. You can see the image is firstly divided into lines and then recognized. But OCR alone is enough. After extraction, we apply automatic cleaning scripts that normalize punctuations, convert typographic variants, and remove non-French segments, such as Latin quotations or metadata in the drama, and also repetitive sentences that are too noisy. We then manually inspect ambiguous lines, especially those containing rare ligatures, long S forms, or split tokens caused by their artifacts. And all this hybrid pipeline of automatic and manual correction ensures the result text is clean, linguistically accurate, and well aligned, which provides solid input for normalization tasks. But even with clean parallel data, tokenization poses a major challenge, especially for under-resourced historical languages. So standard bi-level or white-space tokenizer tend to over-fragment old spellings, especially with diacritics, contractions, and lecture splits. And to address this, we trained a custom subword tokenizer used by pair encoding algorithm. And our tokenizer is sensitive to morphological pattern rather than just frequency, allowing it to better segment archaic and modern variants of the same root. And since our corpus includes both historical and normalized form, the tokenizer effectively bridges the gap between variant-rich inputs and standardized output. And we fixed the vocabulary size to 15,000 tokens, which offered a good balance of compression and generalization in empirical tests. The resulting tokenizer is then serialized to JSON format for reproduction. And then we would like to have a model overview. We use a pretty standard transformer-based encoder-decoder architecture with the specifications shown in the table. As you can see, it has 6 layers on both the encoder and decoder sides, 8 attention heads, and dropout set to 0.1. This model, through tests, can efficiently capture long-range dependencies and character-level substitutions. And similarly, we have a table for training configuration. As you can see, the model is trained using Adam optimizer and with a learning rate of 10 raised to minus 4 for 10 epochs. We use teacher forcing with attention masks, and we trained on a single GPU. though it's actually a pretty small model. Padding tokens are ignored during loss calculation and will apply cross-entropy loss with label smoothing. And then we move on to evaluation metrics. We evaluate using both automated and manual metrics. And this includes the blue score, the character error rate, and the average edit distance via Levenshtein distance. In our practice, the blue score is calculated at the sentence level with 4-gram smoothing. Also, the result is shown on the same page. On our test set, the model achieves a blue score of 58.3, a character error rate of 6.9%, and an average edit distance of 3.98, sorry. Here's a representative example from Le Gazette sentences. As you can see, we have here a resource sentences, which is the historical French, a reference sentence, which is the normalized French, and the actual generated sentences from the model. So the model correctly handles the long S and archaic constructions like d'une, but still minor errors remains in the punctuation spacing, especially with the hyphen. And finally, we would like to have a discussion on the result before moving to the final conclusion. I think overall, the model performs well on regular variation archaic characters, but it still struggles with diacritics and rare abbreviations. These small differences affects the character level metrics even when the overall meaning is preserved. And the tokenizer helped a lot, but a lexicon-aware module might help further. So to summarize this project, what we have done here is that we built a high-quality historical modern parallel corpus. We trained a domain-specific subword tokenizer, and then we implemented a transformer-based model. And with that model, we achieved strong normalization result on early modern French. I believe that this work supports better processing of historical French, and it contributes to digital humanities and the corpus building. Ultimately, the full references are in the published paper, but I would like to mention a few key resources used in the project. And that will be all our presentation. Thank you so much for your attention.